All right, guys, so we're talking about infinite series. So infinite series, I want you to remember, are different um, than sequences. Okay, so infinite series, we're going to be adding up all of the terms, right? And seeing, do all of these terms, these infinite number of terms, when added up, do they go to a number, right? So we're going to look at two specific ones. We're going to look at geometric series and telescoping series, and I'm going to just do some examples of these geometric series for you. And then after this section, this will be on the next test, but after this section, we basically spend like 4 sections on how to determine. Right now, we're only looking at 2 types of series. There are a lot of other ones. So we're going to look at how do we determine if they converge or diverge, right? And we're going to develop a bunch of different ones to do so. So I just want to remind you of, let's talk about geometric series. So if we have a geometric series, right, where we're going to be adding up, and it's important to understand where they're starting your K at. It depends on what book you're using, but in this infinite series, this is going to be the form for a geometric series. Okay. This guy right here will equal A over 1 minus R if the absolute value of R is less than 1, meaning if I am between -1 and 1. And you really should look through how they develop this theorem. It's a really interesting way to look at how they develop this A over 1 minus R. And we got to make sure the big key thing when you're dealing with geometric series is that whatever you're dealing with, you have to get it in this form. Okay, so we have to have it look. We have to have K equal to 0, or we're going to need to manipulate it to where it is K equals 0. We have to have A times R to the K. And as long as that R is between -1 and 1, this guy's going to converge to this one right here. If it's not between -1 and 1, then we say that that series diverges. Okay, so we have to be a little bit careful when we're dealing with stuff like this. Okay, so let's look at a couple examples, obviously, of this. That's what we're gonna do, right? So for these, let's evaluate each series or state that it diverges. All right. So let's do this. I want to kind of keep that up there for the first one. Okay, so let's start off with something fairly simple. Okay, so in this case, we'll look at K equals 0 to infinity. Let's start with something like a -1/3 to the K. So I hope this is pretty obvious, right? That this is a geometric series. Stop that. This is a geometric series, right? And we can see, do we have it in the form that we need? Yeah, I think we do, right? We have the K equals 0, right? That's going to be right there. What is my R? My R in this case is a -1/3, and I like to write down kind of what each variable is. Do I have an A? I don't really have an A, right? My A, well, I do have an A. If I had 0, everything would be 0. A is just going to be 1, though. And because this R right here, absolute value of R is less than 1, we know it's going to converge. Okay, so what is this going to converge to? I can actually say that this series is equal to this number. That is the power of this series, is that I can actually say that if I add up all of these terms, an infinite number of them, it is going to equal this number, people. You really need to read through that derivation of this. It's really pretty amazing. So I get 1 over 1 plus 1/3. 1 plus 1/3 is also known as 4/3, right? If you have no idea how I got that, I'm not sure how you're in Calc 2, but I can I can understand, though, because sometimes as you get higher in calculus, it's the easy stuff that gets harder. I can understand that. So let me know if you're not sure how I got that. But I know then that this series actually does converge to 3/4. If I add them all up, then I get 3/4, which is pretty cool to see. Let's do another one. What if it's not in sigma notation? What if I have something like this? 1 plus 2 sevenths plus 2 squared over 7 squared plus 2 cubed over 7 cubed, and so on and so forth. Plus dot dot dot. So I gotta see, I mean, my hypothesis is, right, that this guy is going to be 2 sevenths, which I know is going to converge in because that's between -1 and 1 to the k. But let's make sure, where does my k start? Well, notice your first term is going to be 1. So what is the only way that I can take 2 sevenths to a power and get 1? That's if k starts at 0. So that's, sometimes they'll try and kind of get you with that, and I'll do it too to you. But I must start at k equals 0 for that in order for that to be 1. And so what am I going to get here? This, in this case, a is 1, right? I don't have anything times it. And r is 2 sevenths. 2 sevenths is between, the absolute value of that is less than 1. So I know that this is going to converge to 1 over 1 minus 2 sevenths. 1 minus 2 sevenths is 5 sevenths. And if we flip that guy, flip it good, we get 7 fifths. So this geometric series is going to converge to 7 fifths. Let's do another one. Whoa. All right, so what about one that's a little bit more interesting? Let's say that we start off at k equals 3 to infinity, 3 times 4 to the k, all over 7 to the k. All right, so this is going to be what we want to look at here. This can be kind of difficult to see because this is going to mess with what our a is and what our r is. It looks to me like r is going to be 4 sevenths, but we just want to make sure that that is true, okay? If you look up here at our infinite series, and if you look at how this is written, let's take this guy right here and let's look at what would happen if I put in k equals 0 and then k equals 1 and so on and so forth, right? So if I write this out, when you put in k equals 0, notice my first term, right? If k is 0, I've r to the 0 is 1, so I just get a. Then I have plus a to the r, or a times r, not a to the r, a r squared plus dot dot dot. So when you're dealing with something that doesn't start at 0 and isn't as straightforward, a really useful way to figure out what your a is your a is always going to be whatever that first number is right here. And then you want to look at that next term and see what your a times r is. So I'm going to do that for this guy right here. So what is my first term going to be? My first term is actually going to be, right, I'm starting at k equals 3. So I'm going to have 3 times 4 cubed. This one's going to be nuts. All over 7 cubed, right? Then I would have plus 3 times 4 to the what? 4th over 7 to the 4th plus, of course, right, 3 times 4 to the 5th over 7 to the 5th, and so on and so forth. So if I compare that to a plus AR plus, what would this be? AR squared plus dot dot dot. This is going to help me see what my A is going to be and what my R is going to be. So in this case, look at what your A is going to be. Your A is actually going to be 3 times 4 cubed all over 7 cubed. I'll figure out what that is here in a minute. And then here, notice that means I have a times my r. So what would, if I rewrote this guy, here's my a, it'd be 4 cubed over 7 cubed, right? What would my r be? Well, I had 4 to the 4th, so it'd be 1 more 4 sevenths. So it looks like my r is what I thought it would be. It'd be 4 sevenths. And this guy here, the absolute value of it is less than 1, therefore it's going to converge, right? And just because I don't have a calculator right on me, what is this going to converge to? So I have this series. I'm not going to be lazy. I'm going to go ahead and rewrite it. I would have 3 times 4 to the k over 7 to the k. This is going to equal my a, which is 3 times 4 cubed over 7 cubed all over 1 minus r, 1 minus 4 sevenths. So I have 3 times 4 cubed over 7 cubed. This right here, this is why I knew in the back of my mind I should wait to simplify this. This is 3 sevenths. If I flip that, that's 7 thirds. So my 3's cancel out, right? And one of my 7's cancel. So 4 cubed is 64, and 7 squared is 49. That was nice. Oh, that's great. That's good. I hope that makes sense. That's a really easy way to do it. You know, when I've taught this in the past and when I've done things in the past, I've like manipulated the k kind of to figure out how I could get that to be 0, and I've pulled off terms, but I really like this way that your book shows. We know that a geometric series, the first term will always be a. So if you can write out that first term, then you're going to be set. You'll be able to figure out what that geometric series is. Let's do one more geometric, and then I'd like to do maybe a couple telescoping, and then we will call it good. So, and this one's going to involve not only just one geometric series, but let's look at, what are we on? Was that C? Oh, the letter alphabet. A math person, come on. At least go by Greek alphabet if you're going to give me something. What if we had something like this? So we have k equals 1 to infinity, and say I have 2 times 3/5 k plus 3 times 4/9 k. All right, so this is a series. These are 2 series added together. Definitely look geometric. I'm raising a fraction, raising a number between -1 and 1. Well, it could be bigger than 1, 2. That's okay. This series could, I'm giving it away a little bit, this series could diverge. That's a possibility. But really what I want to do is I want to show you that we can break these up, right? This is a property of series because we're adding everything together, right? I could think of this as 2 separate series. And if I can find what the first series converges to and what the second series converges to, if it converges, then I can determine what the whole series converges to. Also, if one of them diverges, but one converges, this whole thing is going to diverge. Like, let's say that this guy went to infinity, right? It does not go to a specific number as you add them all up. Then that whole thing, guys, is going to diverge, okay? So let's look at these kind of separately. I'm going to mess with this just like I did before. If k is 1, I get 2 times 3/5, right? If k is 2, then I get 2 times 3/5 squared plus ... So in this case, it looks to me like a is 2 times 3/5, or that one I can simplify, 6/5, and r is 3/5, right? Which is less than 1, or between -1 and 1. So therefore, it's going to converge. And I'll figure out what that converges to here in a minute. If I look at this series right here, right, when k is 1, I get 3 times 4/9. Plus, when k is 2, I get 3 times 4/9 squared plus ... So I know my first term is always a. So a is 3 times 4/9. Or 3 goes into 9 3 times. So my a is 4/3, and my r in this case is 4/9, right? Cool. So this guy converges also. That's great. So we know that then, because both of these converge, I don't know yet what it converges to, but I know for certain, right, that if I have 2 series and I'm adding or subtracting them, and both those series converge, then my series itself will converge. So let's figure out what those are going to converge to. So my first series, I'm going to have a, which is 6/5, all over 1 minus r. And then over here I have plus my a, which in this case is 4/3. I feel like maybe I shouldn't have simplified that. Oh, well, that's okay. 1 minus 4/9 on the bottom. So let's simplify a little bit. So I'm going to have 6/5. This right here is 2/5, but flipped is 5/2. Oh, that's lovely. Isn't that great? It's like it was meant to be. Plus, and this will be 4/3 times this guy here. 1 minus 4/9 is 5/9, but flip it, we get 9/5. Okay, so we get 3 plus, 3 goes into 9, 3 times 12/5, it looks like. So 3 times 5 is 15, 15 plus 12 is 27. So this guy converges to 27/5. That was fun. I like that one. That was great. Good. Okay, guys, couple examples with the telescoping series, and then we'll call this good. I like doing the telescoping. They're a good time. But that's because it usually involves partial fractions, and I know this is not news to you. I enjoy partial fractions. All right, so again, I'm just going to do some examples for you, and then we will, we'll call it good. So let's look at a quick example. Maybe we'll just do one. But the idea with the telescoping series is it's like a telescope. If you take a telescope and you open it up, right? It's all long, but then you can take that telescope and when you close it, it compresses. That's the idea of what a telescoping series is going to do. So let's look at something like this. All right. So the telescoping series, what you want to do first is you want to figure out a different way to write this guy right here. And if I give you a telescoping series, I'll say something like, for the following telescoping series, determine if it converges or diverges. And so that's going to give you a hint that you should do the following thing. So the following thing I'm talking about is we are actually going to rewrite this as a partial fraction decomposition, right? So I have two linear factors in the denominators. Remember this from before. So I'm going to do a over 3k plus 1, right? Plus b over. So that partial fraction decomposition was not only helpful for when we were, oh man, usually I can talk and write when we were integrating, but it's helpful now. So you should know how to do this. I'm going to multiply both sides by the common denominator, which is 3k plus 1 times 3k plus 4, right? I'm going to just go ahead and simplify this instead of plugging in k values, but I would have 3ak plus 4a. Remember, this is a polynomial in k. 3bk plus b. And so if I add up the k's, this looks like 3a plus 3b must be 0, right? Because I don't have any k's on that side. And then this also tells me that 4a plus b must equal 1. So if I look at this guy right here, that implies that a equals negative b, and then I'm going to just plug that into this equation right here. So that would be negative 4b plus b equals 1. If I simplify that and solve, it looks like b equals what, a negative 1/3? And that would mean that a then is a positive 1/3. Okay, so let's rewrite our series. So our series then is going to go from k equals 0 to infinity, and I'm going to have 1/3 all over 3k plus 1, right? And then I'm going to have minus 1/3 all over 3k plus 4. Okay, and I want to figure out, I want to look at these terms. I want to see if I could possibly, again, if it's a telescoping series, that means that everything kind of, stuff is going to cancel out really nicely, right? That's what should happen. And I could even, if I wanted to, and I think I will, I'm going to go ahead and factor out a 1/3 there. Well, actually, I'm not going to do that quite yet. I'll deal with that. Everything adds a 1/3, so I sure could do that. But let's kind of see what happens here. So let's start taking our terms. So when k is 0, that 1/3's bugging me. I'm just going to put it on the bottom. That's the same. 3 on the bottom, so I got a 1. Okay, so let's start doing this. So when k is 0, and I'm not going to simplify. When k is 0, right, this first term right here, I get 3 times 1, which is just 1/3. Here, when k is 0, I'm going to get 4 times 3, which is 1/12. Okay, plus, okay, when k is 1, I'm going to get 1/12. Minus, and when k is 1 here, I'm going to get 7 times 3, which is 1/21. I'm going to keep going just a little bit. I'd like to go a few more than usual, but so this is k equals 0. This is k equals 1. Let's just look at k equals 2. It looks like I get 1/21 minus 1/30, I think. Plus dot, dot, dot. Oh, thank the math gods for the dot, 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 right? Oh, whoa. That's... and I'm sorry, I meant to put here that this is my S sub n. Sorry, nth partial sum. I got a little too excited here. So my nth partial sum, because remember to find the limit of a series, you guys, you have to find the limit as n approaches infinity of the nth partial sum. I'm a little too excited about doing the telescoping series. So the nth partial sum means I'm adding up the first n terms of the series. So let's look at when k is n minus 1. So if I put in n minus 1, I'm going to get 1 over 3 times n minus 1 plus 1, right? Minus 1 over 3 times n minus 1 plus 4, okay? And then when k is n, the first n terms, I would just get 1 over 3 times 3n plus 1 minus 1 over 3 times 3n plus 4. Okay, so take your time with these. Don't be lazy, right? We can already see nice stuff is going to happen. Well, right away, notice I can see some stuff is going to cancel. If I got rid of these parentheses, which I could because it's all addition, I have a negative 1/12, whoops, plus 1/12, that's gone. Negative 1/21 plus 1/21, that's gone. Same thing's going to happen with that negative 1/30. Now here I'm just going to verify that this is going to happen over here. If I multiply this out, this is 9n plus 3. And if we do the same thing over here, right? This inside is 3n minus 3 plus 4. So that would be 3n plus 1 times 3, which is that 9n plus 3, right? So these two terms are the same and are going to cancel. You could verify, if you just weren't sure, you could go and put in k equals n minus 2, and you'll see that guy will cancel. So I have a formula then for my nth partial sum, which is always the goal when we're dealing with series. Okay, so if you look at the development of the geometric series, you'll see they developed what that nth partial sum was, and then they proved that it converges for areas between -1 and 1. I think this is my only telescoping one I'll do because we're already at almost 22 minutes. So what do I get? I get 1/3 minus 1 over 3 times 3n. I'm glad I left the 1/3 in there, plus 4. Okay, I know that that's my nth partial sum. To find the limit then, to find if this series converges, I take the limit of the nth partial sum, which this is great. I want to say it's good news, but it doesn't matter if we converge or diverge. I just feel like when it converges, I've done the work for something at least, right? It converges to a number. What's happening to 1/3 as n goes to infinity? It's staying at 1/3. What's happening to this whole thing as n goes to infinity? Well, the top's staying at 1. The denominator is growing huge, so this guy is going to 0. So what do we know about this telescoping series? That it converges, and it converges to 1/3, or it is equal to 1/3. I have found that this series is 1/3. Okay. All right, you guys. Well, I hope that worked well for you. I was going to prove to you that 0.9 repeating was 1. I didn't quite get there, but I think they talk about that in your book. 0.9 repeating, I just want to show you this. 0.9 repeating, right? I don't know why I put it there. I could rewrite 0.9 repeating. I just have to show you this because I know there are people out there who don't believe that 0.9 repeating is 1. I could write this, you guys, as a geometric series. Look at this, right? 10 to the 4th plus ... Everyone agree with that? This would be 0.9 plus 0.09 plus 0.009. If you're still with me, thanks. Plus 0.0009, right? So I hope you all agree that 0.9 repeating I could write as a geometric series. Well, look at you guys. What is my geometric series? My A is 9/10. My R, right, is going to be 1/10, right? Because here, this guy right here, that's 9/10 times 1/10. Okay, so what is the geometric? Then my R is less than 1. So I know it's going, that whatever this number is right here, which I've rewritten as a geometric series, is going to converge to A over 1 minus R. And in this case, that would give me 9/10. Guys, this is so exciting. It actually really does, I might be a bit of a nerd. It makes my pulse race a little bit. Sorry, A is 9/10, R is a little too excited there, 1/10. So I know then that this geometric series converges to 9/10 over 1 minus 1/10. So that's 9/10 all over 9/10. What is 9/10 divided by 9/10? It's 1. People, 0.9 repeating is equal to 1. We've just proven that using a geometric series. Isn't that neat? Go show your friends. All right, guys, let me know if you have questions.